Hello, welcome to Electronics Education. This is Vincent Chang. Today we're going to start a new series on the subject of frequency response. Frequency response of amplifier. Part 1. The 3 frequency band explained. Frequency response of amplifier. So before we start, let me just talk to you for a bit. You know, many college students and engineers are very intimidated by this subject of frequency response. I think for 2 reasons. Number one, because we live in a time domain. So if you talk about the time, it's real, right? 1 second, 2 seconds, 3 seconds. But what is frequency? What is 1 hertz? The definition of 1 hertz is the inverse of time, the inverse of 1 second. So it's the reciprocal space of time. So it becomes kind of abstract. So, and then the second thing about, and people got frustrated when they study the frequency response, is kind of too complicated. The confidence was totally destroyed by a lot of math, ugly equation. So I think 2 things I can help you with. Number one, we focus on, when I teach the frequency response, I focus on the concept, the key concept. We are not looking forward. We don't expect you to come up with the precise, exact solution. Because this subject is not about math. It's not math. So it's not about exact solution. So it's engineering. So in the real world application, you just need to approximate. You just need a good estimation. So if you are not satisfied with your hand analysis, estimation, or feeling, or intuition, then you use the computer simulation, right? So we focus on the concept. Number 2, we focus on analysis by inspection. So that's 2 things I can help you with. So I'm very excited to teach you about this subject. So I have developed a series of lecture videos. I hope you can learn something, lay a strong foundation in this area. So let's quickly review what we learned before in other courses or lecture video. S-domain analysis, complex frequency domain analysis. We use the S equals J omega, the concept of impedance, to deal with the R, L, C component. And then based on if you, for example, you replace the C by 1 over SC, replace L by SL, then you dive in the circuit based on the circuit theorem, then you derive the transfer function. And then you remember, you have to, once you get the transfer function, you have to replace S by J omega. Omega represents the physical frequency. Then the complex transfer function shows up. So just as you deal with the complex number in the math, you deal with the transfer function in electronics, use the same concept. You deal with 2 parts. One is the magnitude frequency response. The other one is phase frequency response. And let's quickly review the single time constant low pass. This is the transfer function you are supposed to be very, very familiar with. The denominator polynomial 1 plus J omega over omega p. So when signal comes in, 2 things is going to change. One is the magnitude, the other one is phase. But how the magnitude will be changed, it depends on what kind of frequency. It depends on your signal frequency spectrum. And then low frequency pass, the high frequency decay. So it's low pass. And then how much phase will be involved, will be added upon the signal. So it depends on, you have to look at the phase response. In summary, for the single pole transfer function low pass, the phase shift will be involved between 0 degree to negative 90 degree on this type of phase response, right? So now let's look at the common source, MOSFET common source amplifier. So the lesson you learned before is the small signal analysis at median frequency band. At the median frequency band. So you can have the VO divided by VGS and times the VGS divided by VI. So remember the analysis by inspection, VO divided by VGS based on Ohm's law, negative GM, RD, RO, and RL, the three resistors parallel combination. And then the second term is the voltage divider between R and the Rin. So if you struggle with the analysis by inspection, maybe you still need to depend on this equivalent circuit. This type of equivalent circuit is the mid-band, is the equivalent circuit at the median, in the median frequency band. So it's called mid-band analysis. So the gain I was reciting, the gain I was mentioning was the mid-band voltage gain. So again, the equivalent circuit you learned before is the mid-band equivalent circuit. So the gain value, the AM, the M represent the mid-band voltage gain. In decibel scale is the 20 log AM. So it could be 10 decibel, 20 decibel, or 40 decibel. So, and then in the medium frequency band, in the mid band, again, remain as a constant. But when you increase the frequency, because this is the low frequency signal, right? This is the medium frequency signal. But when you increase the signal frequency goes high, like this, and then the amplifier is hard to catch up, right? So the ability to amplify signal, the ability to amplify the signal will be decay at high frequency. So it's the high frequency decay. So same thing, if the signal is kind of low, it's very, for the low frequency signal, the gain will also be attenuated, will also decay. So describe, sometimes in engineering, we are not very interested in the mathematical behavior of this type of performance. But we want to know the 3 decibel frequency, half power frequency. So we want to know the upper 3 decibel frequency, omega h, or lower 3 decibel. So 3 decibel are supposed to comparing to the mid band. So this defines gives you the definition of 3 decibel bandwidth of the amplifier. The 3 decibel bandwidth of the amplifier. Let me show you one example. This is the mid band, the by simulation result for MOSFET common source amplifier. The 20.6 decibel is the mid band gain. But if you just sweep the frequency in the frequency domain from 10 Hertz, 100, and 1K, 10K, 100K, you will get this. So, and then you count the 120 decibel, you count 0.6, deduct 3 decibel, so see the 17.6 decibel, you can pinpoint 2 frequencies. The distance is defined as the 3 decibel bandwidth. In this case, it's 128 kilohertz. So now, let's go a little bit, let me explain what happened to the amplifier. This is the key point of this lecture, okay? Listen carefully. The key concept of this lecture. This is the high frequency band, 3 band, right? So medium band and high frequency band, and this is the low frequency band. on the left-hand side. So when you conduct analysis in the high frequency band, so it's called high frequency response. So when you conduct a signal analysis in the low frequency band, it's the low frequency response. So maybe you are wondering why the gain will decay at high frequency. There's a source. There's a cause. The major cause is because the internal capacitor. Okay? Remember, this is the frequency dependent, right? So it must relate it to the frequency dependent component. What component? The internal. The internal or external are supposed to, with respect to what? With respect to the device, the semiconductor device, the MOSFET. If the capacitor within the device, I call it internal capacitor. But it's the outside the device is called external. So in this case, the CC1, CC2, CS are the outside. But for the inside is this. You learn, I suppose you have learned the semiconductor device high frequency model, right? Five capacitances, the 5 capacitors involved. Those are the high frequency device model. High frequency device model. If we just neglect the 3, the CGB, SB, and the CDB, only focus on the CGS and the CGD gate to source, CGS, and the gate to drain, the CGD. So what is this equivalent circuit stands for? This stands for the equivalent circuit when the amplifier is operated within what frequency? What frequency? High frequency. So this type of equivalent circuit is called high frequency equivalent circuit. It's called high frequency equivalent circuit. And then if you move on the other side, the low frequency end, then why the gain will decay in the low frequency? Why? This is because it's also the frequency dependent behavior, right? So another frequency dependent device is influence the performance of the circuit. What type of frequency dependent device? Is the external one, the external capacitor. The two are coupling. The CC1, the CC2 are coupling capacitor. And the CS is the source bypass capacitor. So it's because of the coupling, external coupling, and the external bypass capacitor. So if you do the S-domain analysis, okay, something ugly is going to show up, all right? If you conduct the S-domain analysis, the slide, I think it's the number 2, right? Number 2 of this lecture. The slide number 2 of the lecture, you replace the CC1 by 1 over SCC1, and 1 over SCC2, and 1 over SCS. And you dive in to conduct the circuit analysis, you're going to see this. You're going to see the 3-pole transfer function pole in the denominator. And the 3-0, 2 at DC, 1 at negative omega LZ in the numerator. So this is the low frequency, the transfer function derived in the low frequency domain. So it's the low frequency transfer function. So now you get a big picture for the frequency response of the amplifier. So again, the lesson you learned before is the mid-band analysis. The circuit analysis is conducted only within the median frequency band. All right, so here's the major takeaway of this lecture. Frequency response of the amplifier. The gain you are supposed to be very familiar with is the mid-band voltage gain. So in the mid-band, it's almost a constant, right? Within the mid-band, the spectrum. But at a high frequency, it will decay. And then low frequency will also decay. 3 decibel bandwidth is the distance between omega h and omega L in the frequency domain. And the high frequency response is caused by what? By the internal capacitor, like CGS of the device, gate to source capacitance, or gate to drain, those type of parasitic capacitance of the semiconductor device. And the external and the low frequency behavior is dominated, is affected by those external capacitor, like the coupling and the bypass capacitor. All right. In electronics, again, we are not very interested in the mathematical behavior of the when things get very ugly or complicated. But what we want to roughly know how far the frequency can be pushed, right? So how far, then we define the 3 decibel, upper 3 decibel frequency omega h, and lower 3 decibel frequency omega L. All right. So in the future, I'm going to teach you a very easy way, a simple way. It's kind of easy. It's called time constant method to quickly estimate the upper 3 decibel frequency. It's called open circuit time constant to deal with the omega h at high frequency. And on this end, it's called short circuit time constant to deal with, to quickly estimate the lower 3 decibel frequency. Again, don't be intimidated by this area, okay? So I look forward to seeing you in the next 2 lecture video about the time constant method. Thanks for watching.